section of the afternoon with Professor Apala Majumdar from the University of Bath, who will talk about nematic application of the polygons from Landau. Thank you.
Okay, so before I start, I'd like to thank the Isaac Newton Institute and the four organizers, Zarnescu, Slastikov, Chen, and in particular Miha, for inviting me to be part of the scientific committee and also being very supportive of my suggestions for this organization of Women in Material Science event. So Carme has introduced me, and as you can tell from my title, I mainly work on the mathematics and modeling of nematic liquid crystals, largely in a continuum PDE-based framework. Now, I know we have several experts in the audience, but always for the sake of completeness and in case there is somebody in the audience who does not work squarely on liquid crystals, I would like to briefly mention that liquid crystals are materials that are somewhere between solids and liquids. We've had several excellent lectures in the past few days, so most of you will know that there are several kinds of liquid crystals, but I largely work with the simplest kind, which are nematic liquid crystals. Now, for the purposes of this talk, all we need to remember, from my point of view, is that nematic liquid crystals, we can think of them as being partially ordered materials, or somewhat soft materials with a degree of long-range orientational order, or the concept of some preferred directions. And because these are directional materials with preferred directions, this actually makes them very susceptible, very sensitive to external effects, like light and external electric and magnetic fields. And notably, it is this direction-dependent response to external stimuli that made them the working material of choice for the multi-billion-dollar LCD industry. Now, in terms of the questions that I work on, I largely work on the mathematics, just a mathematical description of this concept of partial or orientational order. I work with continuum, macroscopic, coarse-grained theories. I've done a fair bit of work on the theory of defects and also on the passage from microscopic to macroscopic derivations. In particular, Professor John Wall mentioned some of the work that we had done in going from the Meyer-Soppe theory to the Landau-Dijen theory, and also, very importantly, trying to have more mathematics-driven approaches to perhaps designing even new materials or even new devices, which is very much in the spirit of this program. So in terms of the outline of this talk, I plan to organize it as follows. So I'm going to start off with a brief description of a real device, which is a planar bistable device that was manufactured by a group in Nottingham, Trent. Then I'm going to talk about the modeling of this device, first in a two-dimensional framework, and effectively describe the stable textures that you can observe in a 2D framework, with special emphasis on a new pattern that we both numerically and analytically discovered. Then I'm going to talk about a fully 3D model, a three-dimensional model, and the differences between the 2D and the 3D framework. And finally, if I have some time, I'd like to talk about some more recent work on ferronematics, which has been done as part of my DST UKIR project with IIT Delhi in India, and then just some future perspectives. So I'm going to start off with a brief description of this, what they call the planar bistable liquid crystal device. So this was first reported in a paper by Sakonas, Davidson, Brown, and Mottram in 2007. So if you look at the picture, the basic construction is fairly straightforward. You effectively have a three-dimensional periodic array of square or rectangular wells filled with nematic liquid crystals. So for a mathematician, this is a fantastic geometry, is square or rectangular wells filled with nematic liquid crystals. But these wells were experimentally reported to be quite shallow, which means that the vertical dimension is actually quite small compared to the cross-sectional dimensions according to the experimentally reported results. And quite importantly, if you do liquid crystals, and we've heard quite a few of these liquid crystal talks, we really need to worry about boundary conditions. And as far as we know, so these wells, they have surfaces. So in principle, if you think of a closed well, I know the pictures give the impression that the top surface is open, but if you think of a closed square or rectangular well, then you have 6 surfaces. And according to the experimentally reported results, these 6 surfaces, they're treated so as to induce either planar or tangential boundary conditions. So you could ask me, what does that actually mean? Well, it means, so you have your 3D box, which is your square or rectangular well. This box will have 4 lateral surfaces and a top and a bottom, right? There are 6 surfaces. And the planar boundary conditions really mean that when you perhaps look down on the bottom surface, so you look down, what it really means is that the nematic molecules on this bottom surface, which is either a square or a rectangle, is constrained to be in the plane of the square or the rectangle. So it's a planar alignment in the plane of the squares. But therefore on the edges it has to be tangent to the edges. So if you think of a square, there are two horizontal edges and two vertical edges. So on the horizontal edges the molecules want to be horizontal, and on the vertical edges they want to be vertical. So you naturally have some sort of a mismatch or a discontinuity at the vertices. But it was experimentally reported that even this I would say this is a fairly simple geometry, this fairly simple geometry supports at least two different stable states, stable nematic states, without any external electric or magnetic fields. The first state was reported to be the diagonal state, where the nematic molecules, they roughly align along one of the square diagonals. It's fairly simple to visualize. The second one was called the rotated state. So here the nematic molecules, they roughly rotate by 180 degrees between a pair of parallel edges. So the nematic molecules, they're either more vertical or more horizontal in the interior. It's just a more uniform profile in the interior. But what was really interesting from their point of view is that both of these states, the diagonal and the rotated, were actually stable without any external effects. So if you get one of these states and you just leave the device on its own, then it just stays in one of these states without any external electric or magnetic fields. And very interestingly, they also have different optical properties, so they like this. They like systems which have multiple stable states without any external electric fields, and these states, if they have different optical properties, then people get quite excited. So we've been working on this device for a number of years now. It started off with a postdoc in 2012 in Oxford, but as you can see, it's been going on, and we have a batch of papers on this particular device from different perspectives. I won't be talking about all of them, you'll be pleased to know.
Do they get both states, like, does anything change to get from one state to the other?
No, so what would usually happen is you have a periodic array, and you fill them up with nematic liquid crystals, and then you let the system relax. And then you will have a distribution of these states. They're just appearing, yeah. And once you're in a state, you just stay there. But I mean, you are more likely to see the diagonal than the rotated, but you will see both. But in terms of our modeling, so we've been modeling this device within the Landau-Dijen theory for nematic liquid crystals. So you've already seen a fair bit about this. It's a very powerful, it may be one of the most powerful continuum theories for nematic liquid crystals in the literature. In fact, it was one of the reasons, not the only reason, obviously, but one of the reasons for awarding Dijen the Nobel Prize for Physics in 1991. So again, from a mathematical perspective, the Landau-Dijen theory, it's a variational theory. And the effective idea is it's a continuum theory, so as far as I see it, the microscopic details are averaged out by the time you get to the theory. It's a macroscopic theory. It describes the state of a nematic liquid crystal by a macroscopic order parameter, which we call the Q-tensor order parameter. And this is a macroscopic measure. You can think of this as being a macroscopic measure of the degree of orientational order, but obviously there are experimentalists in the audience who will give you far better interpretations. But for me, it's a macroscopic measure of the degree of anisotropy in the system. And being a mathematician, this Landau-Dijen Q-tensor order parameter, from my perspective, I see it as a symmetric, traceless, 3x3 matrix with 5 degrees of freedom. So I'm effectively dealing with a mathematical object, a matrix, which has these 5 degrees of freedom, and these degrees of freedom contain information about both the degree of orientational order and also the preferred directions of averaged molecular alignment. Now, since I will be using some terminology later on in the talk, I just want to make the talk as self-contained as possible. So we've just seen that the Q-tensor order parameter is a symmetric, traceless 3x3 matrix. So from basic results in linear algebra, you can write it down in terms of its eigenvalues and its eigenvectors, which is what I've done there at the top. So you can see the lambda 1, lambda 2, and lambda 3, these are the eigenvalues. So you can think of these as being a scalar measure of the degree of orientational order. And the n, m, and p, these are the eigenvectors of the Q-tensor. And you can think of these as being the special directions of your nematic system. Now this, even though it's a very simple representation, nematic phases are broadly classified into 3 main categories according to the eigenvalue structure of the Q-tensor. The first case is the isotropic case, when all three eigenvalues are actually equal to one another, but it's a traceless matrix, so if all three eigenvalues are equal, they're actually 0, and that just means the Q tensor itself is 0, so the system has lost all its orientational order and is actually now disordered. It's fairly intuitive. The second case is when the Q tensor has a pair of equal non-zero eigenvalues. So this is the so-called uniaxial phase, and the idea here is that there is one distinguished direction, which is one of the eigenvectors, with the non-degenerate eigenvalue, and the physical interpretation is that this is the uniaxial phase because this is the one single sort of preferred direction of molecular alignment at every point in space. So there's just one special direction at every point in space. And the third case is the biaxial case, where the Q tensor order parameter has three distinct eigenvalues, and effectively there's a primary and a secondary direction of molecular alignment. So it's a variational theory, so we have the concept of a free energy. So there can be many complex forms of the Landau-Dijon free energy, but I largely work with the simplest one, and that's actually hard enough from a mathematical point of view. But if you look at the energy density, you will see that I effectively have two contributions. I have a bulk potential, which is Fb. If you look at my formula, you will see that my Fb, which is the bulk potential, is a quartic degree 4 polynomial in the eigenvalues of the Q tensor. You can see three parameters there, capital A, B, and C. B and C are largely just fixed constants. We don't worry about them. I don't know if that's a good thing or a bad thing, but I just treat them as fixed constants. But the A is actually the rescaled temperature. And the A is important because for A positive, the minimizers of the bulk potential is actually the isotropic. I mean, for A sufficiently large and positive, the minimizers is actually the isotropic phase, the disordered phase. And for A negative, the minimizers of this bulk potential are ordered uniaxial phases. So this bulk potential actually drives the isotropic nematic phase transition in the bulk as a function of the temperature. The second component is what I call the elastic energy density W, and this actually depends on both the Q tensor and its gradient, and the purpose is to penalize any spatial inhomogeneities in the system. And typical forms of W are quadratic in grad Q. This follows from standard principles, frame indifference, material isotropy. But in terms of the analysis that I'll be presenting and the numerics, we've largely been using the one constant approximation for the elastic energy density, which is just grad Q squared. This is the standard Dirichlet energy density. And in that case is actually, so this is a paper this is from Majumdar and Zarnescu, but it was done before. It's a regular exercise in the calculus of variations to show that all the physically, the modeling hypothesis is that the physically observable configurations, they correspond to either global or local energy minimizers. That's the modeling hypothesis. But you can prove that actually all critical points, not just minimizers, they're actually classical solutions of the associated Euler-Lagrange equations, which I've written down here. And the associated Euler-Lagrange equations, if you just look at the slide, this is what makes this a hard problem mathematically. It's a system of 5 nonlinear elliptic coupled partial differential equations. And it's a hard problem, so these are all classical solutions, so you have a lot of regularity, they're actually analytic, but it's a hard problem because there will typically be multiple solutions. For a given boundary value problem, you will typically have multiple solutions, and for applications, it's not just the minimizers, but you're actually also interested in non-minimizing solutions. And this makes the solution landscape very rich, as you will see as I progress through my talk. So what have we actually done? Well, the first thing we did was to remember my actual domain. So in principle, I have a periodic array of square or rectangular wells. So I just look at one rectangular well. So that's a 3D box, right, from my perspective. So I have a top, bottom, and 4 lateral surfaces. Now, as far as I understand, these wells are shallow. So in the first instance, we are going to be working in the thin film limit, which is where we assume that the thickness, the height of the box is actually very small compared to the cross-sectional dimensions. Then we are quoting a result, from Montero, Golovati, Sternberg, and later there's been more work by Novak, in which at least they rigorously prove using gamma convergence that in this thin film limit and for Dirichlet boundary conditions on the lateral surfaces, so on the lateral surfaces you fix the Q tensor, and on the top and the bottom we use a surface energy but for the right choices of these Dirichlet conditions and the surface energies on the top and the bottom and in the thin film limit, it's actually enough to not look at the 3D box, but actually just to study the problem on the bottom cross section. So you've gone from a 3D domain to a 2D domain. It's also okay to assume invariance in the third direction, so you don't actually need to worry about derivatives in the third direction. And quite importantly, we can assume that all physically relevant states will have one fixed eigenvector in the Ez direction. So if you look at this formula, you have Ex, Ey, and Ez, Ex, Ey, and Ez. These are the unit vectors in the three coordinate directions, but they prove that physically relevant it is reasonable to assume that all physically relevant configurations will have one fixed eigenvector in the Ez directions. And once you have all these reductions, you've gone from a 3D domain to effectively just a square. You can now neglect derivatives in the Z direction, and you have this information that you're restricting yourself to Q tensors which have one fixed eigenvector. You've gone from your Q tensor, which has 5 degrees of freedom, to an object which now only has 3 degrees of freedom. So there's already some model reduction here. You're studying a simpler problem. Well, it's not necessarily simpler, but it's certainly reduced in this thin film limit. So for the first half of my talk at least, I'm now going to restrict myself to Q tensors which only have 3 degrees of freedom, which only depend on the coordinates in the xy plane. And I'm effectively just going to study a boundary value problem for these 3 degrees of freedom, which are Q1, Q2, and Q3, because N1, N2, and Ez, these are just constant unit vectors. So my mathematical problem is now reduced to a boundary value problem for Q1, Q2, and Q3, effectively on a square, subject to fixed boundary conditions for Q1, Q2, and Q3. Now the choice of these boundary conditions for some of you who work on these variational problems is kind of special. What we do is we always work with relatively low temperatures. So we always work for A less than 0, which just means that in the bulk it favors an ordered uniaxial phase. And we choose our Dirichlet conditions on the square edges to be effectively minimizers of this bulk potential for a given value of A. So once we do that, the first question is, do such critical points actually exist? Well, yes, they do. And you can study these critical points, these reduced critical points with just 3 degrees of freedom, as being critical points or minimizers of this functional that I've written up there. This is effectively just the Landau Dijen energy of these critical points. If you look at my formula, you will see a lambda. The lambda is the size of your domain, it's the size of your square effectively. The L is your fixed elastic constant. Now in this work we haven't actually played much with L, it's treated as fixed. And then the rest you've seen. The A is your temperature, and the B and the C are fixed material dependent constants. Now the first thing you can prove is that the first thing that we have proven, which is now submitted to a journal, is that for every A less than 0, we can prove the existence of a locally stable, which for people who are perhaps for a physically relevant Landau Dijen critical point, which has negative Q3 everywhere in your domain. So you could ask me, why is that important? Why do you need negative Q3? Well, Q3 is the eigenvalue associated with Ez, which is one of the fixed eigenvectors, and this result is physically telling you that there is a physically relevant critical point with negative eigenvalue associated with Ez, which means that the molecules are really in the plane of your square. So there is a physical interpretation of this result, that you have these physically relevant critical points which have this in-plane behavior. Now you can go a bit further. We can actually prove bounds for Q3 as a function of the temperature A, and our proof actually follows, this particular proof actually follows quite closely work done by Ignat, Huygens, Slastikov, and Zarnescu, who were working on a disk. So this was very useful for us because we could use the methods, although our domain is different, but we could use the methods, it was quite elegant to get these bounds for Q3 in terms of the temperature. But what stands out from these bounds is that if you work at a special value of the temperature A, which is minus b squared over 3c, we don't fully understand why this is special, but they had the same result as well. So mathematically it is special. I don't know if it is special physically or not, but mathematically it is special because you can prove that at this value of A, your Q3 has to be a constant. And if your Q3 has to be a constant, our life is even simpler because we've gone from a problem with 3 degrees of freedom to just 2 degrees of freedom, because the Q3 is a constant. So now we are effectively just studying critical points with 2 degrees of freedom, Q1 and Q2, on a square domain subject to Dirichlet boundary conditions, and mathematically this is equivalent to actually studying solutions of this system of PDEs, this system of coupled elliptic partial differential equations with just one parameter lambda, which is the size of your square, and some of you will recognize this to be the Ginzburg-Landau PDEs in superconductivity, which means that you can use a lot of results. Now if you look at my system of PDEs, I've told you that I'm largely treating L, which is your elastic constant, and the B and the C to be fixed constants, and my only parameter here is L, which is lambda, which is the size of your square. So the physically relevant question that I'm addressing is, how does the solution landscape change as a function of the size of your square domain? And that is a physically relevant question. And of course, as a mathematician, there are 2 asymptotic limits where you can actually prove things rigorously. So the first one is actually the small lambda limit. You can study the asymptotics as lambda tends to 0, right? Which is effectively when your square is really on the nanometer scale, maybe 100 to 200 nanometers, is kind of small. In that particular limit and at this particular fixed temperature, and this is actually a general result, you can prove that the Landau-Dijon energy functional actually has a unique critical point. So there is just one critical point. So if you find one, you have actually found the global minimizer. And we have analytically shown, and numerically, this was actually first a numerical result with Samo-Kraj from Ljubljana, on which we have done further analysis. But we have actually proven that there is a Landau-Dijon critical point, which is actually the minimizer for small lambda, which we call the well-ordered reconstruction solution, which just actually does not even have it only has 1 degree of freedom. So not even 2 degrees of freedom, just 1 degree of freedom. So if you look at my formula there's only 1 degree of freedom, which is this function Qs. And this function Qs is actually a solution of the Allen-Kahn equation. Now from an experimentalist point of view, I think this result is interesting. So this is a mathematical result. But it's interesting because this particular critical point has a constant set of eigenvectors. So the eigenframe never changes. This function Qs is kind of special because we can prove that it actually vanishes along the square diagonals. And if the function Qs vanishes along the square diagonals, physically this is actually a negatively ordered uniaxial cross running along your square diagonal. So this is it's like a defect cross, right, sort of connecting the 4 vertices of your square domain. And this is why I think this is interesting. And of course, what it actually does is that it partitions the square domain into 4 distinct quadrants, and each quadrant has a constant director profile. And I think this could potentially be interesting if experimentally realized. So our first contribution was actually first the numerical discovery with Samo-Kraj in 2014, and then later analyzed with Giacomo Canavari and my graduate student Amy Spicer, of this well-ordered reconstruction solution in these square domains, which actually exists for all lambda. It exists for all square sizes, but of course we've proven that it is globally stable for lambda small enough, which is really on the nanometer scale. We can prove that it is unstable for large lambda. So as lambda increases, as your square size increases, we can prove that it becomes unstable. And we think this is very interesting because the eigenvectors are fixed, and you have this distinct negatively ordered uniaxial diagonal cross, which is actually a defect which should manifest quite prominently in experiments if realized. So then clearly the complementary question is, if you have an analysis for small lambda, what can you say for large lambda? What can you say for big squares? And for liquid crystal people, a big square is really on the micron scale. Anything on the micron scale is big. Now here the results are more expected, I think. So for people who are familiar with these techniques, you can probably prove that as lambda gets very large, Q1, Q2, which are the only 2 degrees of freedom, that actually tends to a vector field of constant magnitude, and there is just effectively one angle theta, which is the in-plane alignment of the nematic molecules in the square domain. And to leading order, the problem is really a solution of the Laplace's equation on a square or a rectangular domain subject to prescribed Dirichlet boundary conditions. It's just the Laplace's equation for theta. And theta is effectively the in-plane angle of the nematic molecules in the square. And this was done with my first graduate student in Oxford, but I think the punchline is that you recover the diagonal and the rotated solutions in the large lambda limit, which is what you'd expect. So here I have a bifurcation plot. So this is joint work with Robinson, Chong Liu, Patrick Farrell, Radek Urban. This has now been published, but it's really a bifurcation diagram trying to track the solution branches of this 2D problem as a function of the square size. So if you look at the extreme left, you only see one branch, and that's the well-ordered reconstruction branch. Now this loses stability as the well size increases, as we've proven, and that's expected. And then if you look at the extreme right, you see 6 solid lines, and those are your 2 diagonal solutions and the 4 rotated solutions. And you can also track the bifurcation points, which is actually very interesting. And just to give you a flavor of how interesting it might be, we've used some numerical deflation techniques here to actually compute all the critical points of this reduced 2D functional at this fixed temperature for an intermediate value of lambda, which is your square size. And if you look at my pictures, I'm not sure if they're very visible, but you see the diagonal and the rotated right at the top. You see my well-ordered reconstruction solution right at the bottom. And then you see a whole host of other critical points as well, most of which are actually unstable, but they are critical points. So you might be wondering what the blue bits and the red bits are. The red bits, informally speaking, are where the molecules are roughly well aligned, and the blue bits are where they are disordered, but disordered in the plane, which means mathematically they're actually negatively uniaxial. These are actually examples of negatively uniaxial interfaces in the 3rd dimension. But if you restrict yourself to a 2D analysis, these are what you would call defects. I think Miha was referring to these. He had blue regions near various corners on his fractal domains, and he was referring to these as defects. And it's a similar scenario here, but obviously the geometry is simpler. It's a square. So a very natural question is, what happens if you go away from the thin film limit? What happens if you have a real box where you have, the height is not necessarily so small? And it's very natural to ask, will the well-ordered reconstruction solution survive in 3-dimensional scenarios? And the answer is luckily yes. So you can take a full 3D box. So now you have 2 length parameters. You have the size of your square, and you also have the height of your box. And you can impose your Dirichlet boundary conditions on the 4 lateral surfaces and the surface energies on the top and the bottom. And the first question is, do you have a well-ordered reconstruction solution? And the answer is yes. We can prove the existence of a well-ordered reconstruction solution for actually arbitrary values of the well height. And the claim is that this solution is special because it has a constant set of eigenvectors. It has this very distinct diagonal defect cross. It's invariant in the z direction, and it only has, and of course it has only 2 degrees of freedom, and it's negative Q3 everywhere in the domain. So it is relevant in a 3D context as well. We can again prove that it is globally stable, so it is actually relevant as long as the cross-section is small enough. So even for boxes which are quite tall, if the cross-sectional dimension is small enough, this is the relevant solution. I think that's interesting, and there is actually some analysis to be done here. It's not an immediate result. You have to work out a maximum principal argument, you have to repeat the uniqueness argument, but that's interesting. But it does get unstable for large lambda. And that's also interesting because in a 3D context, you're going to get new instabilities. And that's what we found. So when lambda was large enough, we numerically, so these results are numerical now, we numerically recovered what we call new mixed solutions. So when I say mixed, these are mixed in the sense, if you look at my 3 pictures, so on the bottom surface you have one diagonal solution. Right at the top you have another diagonal solution, because remember there are 2 diagonal solutions. And the system mediates between these 2 diagonal solutions via some 2D profiles, which could be the well-ordered reconstruction solution. So the well-ordered reconstruction solution, although unstable in itself, is acting to interpolate between perhaps these 2 different diagonal solutions at the top and the bottom. And we think that's also interesting, that in a 3D box you get these stable mixed solutions which are actually generated from 2D solutions on the different cross sections. So in the last, I don't know how much time do I have? So in the last 5 minutes or so, or maybe a bit more, maybe 7, I want to talk about a relatively new project. It's what we call ferronematics. So this is funded by a 3-year DST UKRI project on theoretical and experimental studies of suspensions of magnetic nanoparticles with IIT Delhi in India. So we have a range of collaborators. We have Professor Milevsky at Bath, Dr. Wang at Chicago, and the principal investigator from India is Professor Banerjee, and it also involves a graduate student, Mr. Bisht. And it's also very much in the spirit of global challenges research funding. So, and that's picking, and I'm part of that as well. But in terms of the actual, in terms of what we're actually doing, so as far as we understand, this is not my main field of expertise, but nematic liquid crystals, they have a much stronger response to external electric fields than they do to external magnetic fields. And in the 1970s, Brocard and Digens, they proposed that if you add magnetic nanoparticles to a nematic liquid crystal, you might potentially get a much stronger enhanced response to external magnetic fields. Now, there has been some stellar work by actually the Slovenian group, Alenka Martej. She was mentioned yesterday, and they actually experimentally delivered these stable suspensions of nanoparticles in nematic media, and we thought that was fantastic. This was a Nature paper. So we are effectively trying to model a similar system, although the exact framework is not quite the same, but we're trying to model a similar system. We're trying to model a dilute suspension of magnetic nanoparticles in an anisotropic nematic liquid crystal. So what do I actually mean? I just mean that the nanoparticles are actually quite small. They're also quite small compared to perhaps the distance between different nanoparticles, and they're uniformly distributed. So this actually may be similar to the sort of theoretical assumptions that have been made in a recent paper by Canavari and Zarnescu. But the approach that we are adopting is different. But we're effectively working with a uniform dilute suspension of magnetic nanoparticles in a nematic liquid crystal. That's what we're trying to model, and we're trying to theoretically investigate whether we can get new textures from the magneto-nematic coupling from a theoretical perspective. So this is our approach. We are trying to describe, and this is not original because I think the paper by Alenka Martej was also, they were also adopting a similar approach. So we are trying to describe this system by effectively two order parameters. First, we have the usual Landau-Dijen Q-tensor order parameter to describe the nematic order, and then we are trying to describe the averaged magnetization, which is coming into the system from this interaction between the magnetic nanoparticles and the host nematic medium by a magnetization vector, a 2D vector. And we're not assuming any constant length constraint. So we have a Q-tensor, it's a reduced two-dimensional Q-tensor to describe the nematic order, and a 2D vector to describe the average magnetization. We are working with a nice square domain. We are imposing tangent boundary conditions or planar boundary conditions on the nematic molecules again, which just means that on the square edges, the nematic molecules want to be tangent to the edges. So this is consistent with everything that I have presented so far. And regarding the magnetization vector, we are assuming that the magnetization vector kind of follows the nematic molecules, which is reasonable because a lot of the literature does focus on the regime where the magnetic nanoparticles like to line up with the nematic molecules. So it's reasonable to assume that on the boundaries, the magnetization vector is somehow going to follow the nematic alignment, and therefore effectively at a mathematical level, we have a Dirichlet boundary value problem for both the Q-tensor and the magnetization vector M on a square domain. And then we are using a continuum approach, so we are postulating, and this is again not original because Alenka Martej had a very similar free energy in her paper with her co-authors, but this is also, I don't think it's identical. It is slightly different by perhaps one term, but the essential idea is the same. We have a continuum free energy, and there are three different contributions. The first contribution is your usual 2D Landau-Dijen contribution. The second one is the energy associated with a spatially inhomogeneous magnetization field, and the third one is the coupling energy between the two, between the Q and the M, which somehow enforces or sort of coerces the nematic molecules and the magnetic nanoparticles to line up with each other. And then because we are mathematicians, we write down the Euler-Lagrange equations, and the work so far has been entirely numerical. We try to solve these PDEs using finite difference methods or using commercial PDE solvers. So we have some results, and we've also submitted a paper, but the one that I think is quite interesting is if you take a square well, so without any of the magneto-nematic coupling for the uncoupled system, the nematic profile would have either the diagonal or the rotated state, right? Because we've just shown them that in the large lambda limit, you expect to see either the diagonal or the rotated state. So let's assume that for the uncoupled system, you start with your rotated nematic state. Now the M vector, if it was just completely left alone, would have this nice vortex structure because of the imposed boundary conditions. And then the question is, what happens when you solve these PDEs subject to these boundary conditions, and you introduce the coupling? So, and remember, your coupling parameter is this C1 and C2, or the gamma in the energy in your free energy. So, what happens as you increase gamma? Do you see a change? And actually, in the nematic profile, based on our numerical results, which will be checked again very carefully, but we have checked it with two different sets of methods. It seems that you can stabilize vortex structures in the nematic by means of this magneto-nematic coupling. And these vortex structures would be unstable without the coupling. But it seems that these vortex structures are actually numerically stable, and this can be checked even with gradient flow, with this enhanced magneto-nematic coupling. And I find that quite interesting, that you can stabilize something which would be otherwise unstable by means of this magneto-nematic coupling. So I'm pretty much at the end of my talk. Just to give you a few perspectives, so everything that I've said is really for a square domain, but in collaboration with lots of collaborators based on a Royal Society Newton Advanced Fellowship, mainly at Peking University, Shanghai Jiaotong and Dalian, and also with Canavari in Spain and Weiwei Wang in Chicago, we have been actually doing similar work on any arbitrary 2D polygon. The methods are actually quite generic. Here I have some results for a hexagon because they're just easier to visualize. But as you might expect, you get more stable equilibria. You have more to choose from as these polygons become increasingly complicated, or they have a larger number of edges. And what's the bigger picture? Well, for me, the bigger picture is I think the well-ordered reconstruction solution is very interesting. It's interesting because hopefully from an applications point of view, it's a new state where you have this distinct defect cross, which effectively partitions the domain into 4 quadrants. From a mathematical perspective, it's that this defect cross is actually a negatively ordered uniaxial interface in 3 dimensions. So it's an example of an interface in a higher dimensional problem. And mathematically, that's quite challenging. It also illustrates new connections, actually, between solutions of the Allen-Kahn and critical points of the Landau Degen energy functional. And it's quite interesting that even though that these solutions, they become unstable for large lambda as the square size increases, the instability is highly localized. So it is possible that we can control these instabilities by means of new control problems. And that actually brings me to the end of my talk. I'd like to thank everybody who's given me money, and thank you for your attention. So thank you.
You have taken Q, the second order tensor Q, as symmetric and also traceless, that is deviatory. So what is the reason behind that? Because in general, in continuum mechanics, for deformation of body, we define Gaussian trace, which is symmetric but not traceless. At the same time, if I consider the change in shape, so change in shape depends on only the deviatory part of the state.
So it measures the deviation from the isotropic state. So if you think of the Q tensor as being the second moment of a PDF, and then you subtract the isotropic part, which is what Professor John Ball was in his talk, you would naturally get something which is symmetric and traceless, because you somehow want to measure the difference between an isotropic where you don't have this orientation. So you're measuring the degree of anisotropy, the degree of orientational order. So you're subtracting something, and that's something, when you subtract this is what gives you the traceless part. But that's a statistical mechanics approach. But also, I think you need 5 degrees of freedom to describe the state anyway. So you have 3 degrees of freedom associated with the eigenframe, and 2 degrees of freedom associated with the actual degree of orientational order. So you need 5 degrees of freedom in the object itself to describe the orientational order.
So in the problem with the square, you use the 3 by 3 Q tensor and reduce it from 5 degrees of freedom to 3 degrees of freedom, right? Have you also considered this, the problem where you actually consider it to be really 2D, so that you describe it by a 2 by 2 Q tensor?
So once you make all that model reduction, it is 2 by 2. So these are, you're talking about this picture, I think.
Yeah.
This one, right?
Is it like a cell that is a square with a really small height?
Yes.
Is it proper 2D?
Yes, so at this point, because all the model reduction, when I did all of my reduction, I was really just left with a square. I forgot about the third dimension completely. I was using the gamma convergence results. So I used the rigorous results to justify this strictly 2D approach. But at this point, when I've computed the bifurcation diagram, I was left with a 2D domain, and I was left with a 2D Q tensor with just 2 degrees of freedom, Q1 and Q2.
But I mean,
if you had a strictly 2D nematic, B would be 0.
Yes,
So
that's
it's
right.
not that problem that you're solving.
yeah, because at 2D it would be also a continuous transition instead of a first order.
So, I mean, so maybe I'm missing. So this is what we've done, right? So this is the Q1, Q2. But I think what Professor Mike Cates is saying, that there is a 3D interpretation, because all of this was done at the fixed temperature where Q3 is. So there is actually a third component. So it is still a 5. You still retain the 5 degrees of freedom, but this Q3 bit is being separated because it's just a constant. And then from the numerical point of view, you just looked at this problem, which just has 2 degrees of freedom, Q1 and Q2, on a square, and treated it and looked at its critical points. And when you say about the actual transition, we're working with A less than, you're pretty much deep in the nematic phase. So this is not trying to just look at phase transitions between, you're already in the nematic phase. This is really just trying to capture what you might actually observe in these systems for low temperatures.
So actually you're looking at the square with a really thin height, but I'm asking what would happen if you would do it really 2D from the start?
You mean just Q1, Q2 with B is equal to 0?
Just a 2 by 2 Q tensor.
So then you would lose the cubic term. If you really do it, you would lose the cubic term. And then there's actually Ginsburg-Landau theory.
Yeah, so what would happen with B tensor?
Well, then you would, then this is exactly, I mean, you would not have the third component. These are your results. I mean, this is the answer to your question. This is strictly that this does not know anything about Q3. These results are purely for Q1 and Q2, for a 2 by 2 matrix on a 2D domain.
Do you have any analysis of this model? Because that non-local term, it's very, very hard to justify. So these are simulations or are based on analysis?
So the
With Antonio and Dimitri Golovati, a couple of years ago, we started work.
So this is analysis. So the paper with Canavari Spicer is analysis. If you go back to the list of publications, yes, I
actually have an error analysis and you justify your numerical method. And can you actually put the interaction term with magnetic field?
Oh, you mean for the ferronematics?
Yes, but especially, well,
Well,
I'll follow up later.
For ferronematics,
That
no,
local term is really very, very, very delicate. So.
From a I mean, for us, it's a system of 4 PDs, system of coupled 4 PDs. I mean, the numerical methods, I mean, he's using Chebyshev polynomials and he's using the energy minimization. I think and he checks the stability by the second variation.
Oh, thank you. Maybe we should move on.